Greetings, I'm Lauria, and I'll be discussing our automatic meshing algorithm for pulmonary airways. The interaction of deformable structures in flow has been modeled in such biological systems as the cardiovascular system, the larynx, and the lungs. Flow structure interactions can even model the way fish fins interact with water, or the way cicada wings interact with airflow. These systems share a similarity: large deformations of biological structures and their interactions with flow. Such a model for pulmonary airways could aid in COPD assessment, normal tissue sparing for lung radiotherapy, or outcome predictions for lung volume reduction surgery. Our overarching goal is to develop a complete pulmonary FSI model. Current models in our group include the elastography model, which is used to estimate tissue elasticity from CT, and our 5D CT model, used to obtain lung deformations based on quiet respiration. We envision coupling these available models with computational fluid dynamics to complete an FSI model of human breathing. Introducing a CFD model requires that we can obtain a CFD-compliant mesh, which we define as carefully triangulated to avoid leakage or blockage of flow due to holes or cross-triangulation. Commercial software exists to create such meshes, but these require time-consuming manual correction not suitable for a clinical setting. Open source techniques often serve as the standard for CFD studies, but lack explicit constraints for CFD compliance that can lead to holes and cross-triangulation. Other research efforts have been made to improve airway meshing, but they either target pre-meshing stages like segmentation or seek to correct an initial mesh. Most importantly, these studies have yet to explicitly address the CFD compliance of the triangulation mesh. We introduce an automatic lung airway meshing algorithm from 3D CTs that has been tested for CFD compliance. Beginning with a fast helical free-breathing CT scan, we can segment the lungs and obtain a smooth centerline skeleton point cloud. Using the skeleton, we detect bifurcation points where the branches split and label the terminal points, which are the points at either end of the branch. We generate unit circles around the skeleton branches and project them to the segmentation outline. We call the projected points radial points, and these serve as our mesh vertices. We then reiterate the terminal point detection so that the segmentation outline points do not intersect. With the new branches labeled and any potential intersecting vertices removed, we mesh along the branches and over the bifurcations with a fixed template to ensure CFD compliance. Starting with the scan on the left, we call the open source Pulmonary Toolkit at the beginning of our implementation to obtain automatic airway segmentation. Then, we implement a 3D thinning algorithm from Lee et al. To obtain a medial skeleton. Finally, we smooth the skeleton using a regularization technique implemented from Huang et al. Beginning with the top of the trachea, the points are tracked to detect bifurcations. Each point is evaluated as x in the equation shown from Huang et al. For each x, the 2 points behind and in front are taken as well as n. If all endpoints satisfy the linearity condition, the point x is considered along the branch and removed from the candidate pool for bifurcations. Because many points will satisfy, we further narrow down the pool of candidates by searching for a point whose 3 nearest neighbors are more than 25 degrees apart. Then we take the most central of those. In the next step, we define 3 terminal points around each bifurcation. Then, we isolate each branch by tracking from terminal point to terminal point. Labeling the branches allows us to treat them in their own coordinate frame and generate the surrounding points based on the geometry of the individual branches. With each branch isolated, we generate small 1 mm radius circles at each point along the branch, such as the red branch point in the figure. The normal axis of each circle aligns with the slope of the branch at that point. For each evenly distributed point on the circle, we follow the radial axis and find the plane of the segmentation outline points. Each point is projected out to the segmentation to give us points that represent the outline. This process ensures that the points are perpendicular to the branch and thus will not intersect during meshing. Having the radial points projected to the segmentation outline, we can now use them to ensure that no cross-triangulations occur between connecting branches. To do so, we simply choose new terminal points that create necessary space between branches to avoid overlapping, which would lead to intersecting triangulation edges. Now we have terminal points that will not cause any blocked flow via incorrect triangulations and radial points to go with them. Pictured to the right are such radial points with the new terminal points in green. With the care taken in the earlier steps, the same number of radial points exist in consecutive circles and at fixed angles. Therefore, we could take one global connectivity map and apply it to every consecutive circle without causing any missing connections or connections across the airway cross-section. Similarly, we can use one large connectivity map to connect the terminal points associated with each bifurcation. Treating these points in an isolated coordinate frame, we reorder radial points around the associated terminal points to be able to map them in any orientation. We then apply the global bifurcation connectivity map, hence adding this template-style feature. To clearly demonstrate the capability of our algorithm, we first ran it on an artificial simplistic model. Shown here are the simulated image, resulting centerline, and finished mesh. The mesh demonstrates clearly the branch-wise meshing style and the bifurcation template mesh. There are complete triangles and no twists or incorrect triangulations. It is therefore fully CFD compliant. Shown here are key examples of the ideal geometry when using our algorithm on the top row and using ball pivoting algorithm in MeshLab on the bottom row. On the left, the first bifurcation is shown and triangles are missing in the BPA mesh. In the next two columns, higher generation bifurcations show more crucial errors, demonstrating that standard meshing techniques can fail our CFD compliance criteria in even the simplest lung geometry cases. Now I'll showcase one patient in detail. Here are the original CT image, the pre-processed centerline skeleton, and the resulting mesh rendered in ParaView. To compare to the standard of open source meshing seen in the literature, we compare our mesh to those resulting from BPA in MeshLab, marching cubes also implemented in MeshLab, and CGAL implemented in the ISO2Mesh code package for MATLAB. Using the meshes in the previous slide, we run a simple smooth particle hydrodynamics implementation of CFD. The only force involved in the simulations is gravity, just to demonstrate that flow can move through the meshes and assess CFD compliance. The leakage in the BPA simulation occurs as soon as the first bifurcation and in several instances after. The marching cube simulation experiences leakage in several fourth-generation branches. The CGAL mesh has shortcomings related to the actual meshing capabilities, and these in fact cause blockages in the bottom right of the mesh. These leaks and blockages are avoided when using our mesh, and flow reaches further through the tracheobronchial tree, demonstrating increased CFD compliance. Here are some zoomed-in examples from the simulations. On the left, a leakage in the BPA mesh is not seen in our mesh. On the right, flow through our mesh moves beyond a blockage in the CGAL mesh. Following the same workflow for 5 additional patients, findings were consistent. In all cases, our mesh was equally CFD compliant or better than the other tested methods. Here we show examples for a leak from BPA, blocked flow from marching cubes, and block from CGAL, where our mesh provided a more CFD compliant geometry for flow simulations. To assess the mesh quality, we have calculated several metrics. The values in the table represent averages across the 6 total patient cases. The first column represents the mean distance from the vertices to the nearest true segmentation point. Our mesh has a smaller distance error than marching cubes and is within 0.02 millimeters of the CGAL error. Note that BPA mean distance to surface being 0 is a fixed criterion of the method. The second column shows the mean distance from each segmentation point to the nearest vertex. In this metric, our mesh is on average within 5 millimeters and is slightly lower than that for marching cubes and CGAL. Mean edge length, skewness, and aspect ratio reveal how small and equilateral each triangular element is. Skewness and aspect ratio values closer to 1 represent higher quality, and lower edge length represents better resolution. These were not improved with our mesh. The important metric for our study is the mean minimum branch level reached by flow and the maximum. These were always highest for our mesh, and ours is the only mesh that reaches a minimum of 3 branch levels on average. Analyzing the mesh element quality in different branch levels reveals that the metrics improve with increasing generation. The first level, or trachea, has skewness and aspect ratios below 0.2, which greatly weighed down the mean value. This is likely due to the radial point sampling remaining the same while the diameter is decreasing, hence increasing the resolution. Therefore, we can improve quality by increasing the point sampling around the outline depending on the branch level or diameter. In conclusion, we have developed a meshing algorithm aimed at meshing lung airway geometry in a CFD-compliant manner. CFD results show that our mesh experiences no leakage and less blockage than standard algorithms, demonstrating more compliance. This algorithm could be applicable for managing COPD, sparing functional tissue during radiation therapy, or predicting surgical outcomes. In the future, we aim to improve the pre-processing quality, such as segmentation or skeletonization, increase the point sampling of the radial points, and have the point sampling vary with generation. Explore the use of implicit surfaces, regularization, or surface blending to improve the quality of the individual meshing elements, and extend the study to a larger cohort, and compare flow in cohorts with and without COPD. I'd like to thank everybody who helped to conceive and execute this study. Thank you for listening.